All right. So we were halfway through a problem. Uh, it was pretty hard. So it was so there was this tank of water that was getting filled with water, and it was a cone because um, math problems have a lot of tanks of water, weird shapes. I don't know who's filling an ice cream cone with water, and the and you're pouring in water, presumably always at the same speed, at 2 cubic meters per second. And if I picture this in my head, I the water level at first in a narrow bit of the cone, the water level rises a lot faster than later. So the question is, when the water level is 3 meters deep, how fast is it rising? So so that's the question. I would guess it's rising as if it was a cylinder. So the thing is, we wrote down all the quantities. We said W is the height, the depth of the water at a given point. So I can't say that W is 3 because it's only 3 at a particular point, but it changes. The amount of water in the cone of water is, I'm calling V, and then the formula for the volume of a cone relates these two, but there's a problem that I that there's the radius is involved, and we didn't figure out what the radius. If I can say anything about the radius, I probably have to. Otherwise, this is gonna go badly. Um, and also we didn't use the dimensions of the cone for anything, so that's probably not great. So so yesterday we were confused. I don't know if anyone thought they slept on it and now they have a better idea. But in the meantime, I'm gonna draw some more pictures. So this is what the cone looks from above. Looks like a circle. And then there's water in there. And this is R. This is the radius of the container of the tank, which is 2 meters. That's really all I can say. From the side. So from the side, a cone is a triangle. It's an isosceles triangle. And the water also looks like a triangle. So the thing is, I should know the radius because there's only one way to draw this triangle. If I look at the picture on the side, if I draw, so this triangle has sides, has a side of length 4 meters, and it has height 4 meters. So there's only one way to draw that. And then if I fix the depth of the water, then the radius, well, there's only one possible. Then That's all I need to do the drawing. And the radius is found here. And if it's uniquely determined like that, that means I should be able to compute it. So the question is how?
Would we just like plug in 3 meters for the volume?
3 meters for the volume?
Yeah. And then like oh wait, no, we don't have wait, we have the height, right? Of the
I have the height, but the thing is the height of the water is changing. So I should say that the height is W. But I can pretend I know W, probably.
could you say like it's a change in W over the change in time?
The radius?
Well no, like the height. Like the it's like dW over like D T
No,
maybe.
the height is just W.
Well well I mean wouldn't aren't we trying to like find it at any particular point that it's rising?
I'm trying to find, so, okay, you're right. What I'm trying to find is dW with respect to dt. The problem is, so the thing is, if I look at this equation, so let's just do it and see what the problem is. Pi over 3 r squared W. If I try to take derivatives, there's going to be, so here I have dv dt, and here I have pi over 3, and now I have a product. So I need to use the product rule. So this is the derivative of r squared dt times W plus r squared times the derivative of W. And the derivative of r squared is 2r times the derivative of r by the chain rule. So this is the equation I have. And now this is 3 cubic meters per second. This is given. This is the depth, which is 3 meters. This was also given. This is what I want. So it's fine that I don't know it because it's what I'm trying to solve for. But now the problem is that there's r and r prime.
Bless you.
Thank you. So so I can solve for W prime, but there's gonna be r floating around. That's the problem. 4 minus W.
You
4
know
minus.
how like geometry we did like the relation thing where like you have like so let's say they have like triangles, you can try and find like the missing side of a triangle by doing like related like A over B is equal to C over D. So could we do that with like the cones?
I think so. I think we're supposed to do something like that because if you look at the shapes of these things, the thing is these two have the same shape, and I think this is sort of what Matthew is doing. That's not going to be 4 minus W because 4 minus W gets smaller as W gets bigger, and I know the radius from the picture. I know R gets bigger. as W gets bigger. So so this is the center of the cone, the axis. And the thing is, these triangles have the same shape. What you used to call them in geometry class that they're similar. So there's a big triangle of height 2 meters, height 4 meters and short side 2 meters. It's a right triangle. And it has the same shape as the smaller triangle, which has height W and short side R. And I know it has the same shape because, well, presumably, I guess no one told me the cone is horizontal. The cone is straight, and water is going to want to have a horizontal surface. And this means if they have the same shape and the long side is twice the short side for one of them, then the long side is going to be twice the short side for the other. So 4/2 is W over R, or however you want to write this. So that means that R is W, R is half of W. So the point of giving me the data of 4 meters and 2 meters is that so that I know. Oh, there you go. That was in the chat. For the for any cone that the water makes, the height is always going to be twice the radius because they all have the same shape. They're all similar. Similar triangles have proportional sizes, proportional sides. So this means if I go like this. So W equals 2R. And well, maybe I'd rather solve for R. So R equals W divided by 2. And taking derivatives, the derivative of R is the derivative of W divided by 2. So now I know R and I know R prime. So I'm gonna be able to solve this. I'm gonna be done now. Just from the equation I had, but so now there's two ways to go about this, and they both work equally well. But so I have these two equations, and I could plug them in here, and I would be able to solve for W prime, or I could plug R equals W over 2 here, which is not a problem because I'm saying R. The problem is if I make W equals to a number, that will mess everything up. I'm not paying attention to the chat today. Sorry. But tell your cat to unmute themselves if they want to speak. So plug in R equals W over 2. If you do that, you're saying as W changes, R changes. And then this is the formula for the volume. So, and then take the derivative. And that's what I'm going to do. It's easier. So I have that V equals pi over 3 R squared W. And also I know that R is half of W, so plug in R equals W over 2. And you will get V equals pi over 3. So W halves times W. And now, since I want to take the derivative of this, I better simplify it. Otherwise, I'm just shooting myself on the foot. Like that Prince of Spain you undoubtedly have heard of. So I have 2 W's and another W combined to make 3 W's. A 3 and a 4 combined to make a 12. So now that I have V equals pi W cubed over 12, I can do what I was doing before, but it's easier. Take the derivative. On the left, you will have dv dt. On the right, the constant can come out, and you have dw cubed dt. And I want to say that this is 3w squared, but this is not. That's not the derivative with respect to w. It's the derivative with respect to t, which means that as every time I have this kind of problem, I have to do the chain rule. So derivative of w cubed with respect to w times the derivative of w with respect to t. I feel like you should be bored of me using the chain rule by now. And now the power rule says 3w squared, and well, this is w prime. This is w prime is what I want, remember. So now I know the derivative of v. I know w at a particular moment that I care about, and I want w prime. So I'm in good shape. V prime equals 3w squared times w prime. I want to solve for the thing. Oh. And the pi over 12. Woof. Pi over 12. So pi over 12 times 3 becomes 4. Pi over 4. So pi over 4.
Why didn't we take the derivative of pi over 12?
Because it's a constant. It's multiplying, and if I multiply by a constant, that I can do that before or after the derivative. Doesn't matter.
Oh, okay.
Pi over 12 is just a number. So this is 4 over pi 1 over w squared times v prime. And I'm told when w equals 3 meters, v prime equals 2 cubic meters per second, and that would mean that w prime equals 4 over pi 1 over 9. I'm going to write the units just to see that I get the correct units. So that is 8 over 9 pi. And the units are meters per second. Should I be getting meters per second?
Yes.
Yeah, because it's the speed at which the depth is changing, and the depth is meters. And if I measure the speed of that, that's going to be meters per second. And that's it.
Wait, is
So,
that 6 pi or 4 pi? Like 4 over pi.
I have
4
an
over
extra 2 there. So I think it's, so I have 4 and I have 2
pi.
in the
Okay.
numerator, and I have 9.5 pi in the denominator. What's the book got? Did the book agree with me? Oh, we did. All right. So
Oh,
I
that's
think,
why you got meters instead of cubic meters. Okay.
yeah, meters. I mean, I'm not supposed to get cubic meters, right? So it's good. I mean, checking units doesn't take a lot of work, and it's good. Makes you realize that, makes you easily see if you made a mistake. So I think the algebra, taking the derivative of w cubed, I mean, compared to like the implicit differentiation I just gave you in the homework, it's very, very easy. The problem, of course, was the geometry bit, the part with the similar triangles. Like it's hard. What can you do? Are there any more questions? Can we do an easier example? I don't want to spend more time in this chapter. I can do it in office hours if you want me to. Because they never take less than 20 minutes. I want to move on to greener pastures. So before doing that, I have to cover 3.10 and 3.11, which, if I'm honest with you, they're kind of meh. And I don't feel this way about most of the chapters. I feel like I tell you when something is interesting and or important, like 4.1 is super important. But these two are like, so I'm just gonna talk a tiny bit about them. And honestly, so this chapter, 3.9, 3.0, 10 and 11, I don't know what I said. This chapter you learn a lot more about if you take Calc 2. What's the last chapter that we go to? Well, you can look at the syllabus. Look at the syllabus. There's, because basically it's 5 and 6, and then we're supposed to jump and do a little bit of 8. But we'll see how that goes. Okay, differentials. So there's this thing you should know about called the linear approximation, which I think in a way you pretty much already told you what it is. So the thing is that the tangent line is the linear function of the graph. So basically the idea is I have a complicated function. First of all, some functions are more complicated than others. The function 3x plus 2 is a linear function, which makes me feel pretty confident that I can understand it. I could compute it pretty easily. The function e to the x is more complicated. Like how's it, like when you put it into a computer, when you write a squared, how is it even computing it? When you write e to the 2.5. So if I could say that e to the x is very close to an easier function, that could make my guessing life a lot easier. And this is actually very similar to what calculators are actually doing. So the thing is, in a graph, you have a function. If the function happens to be differentiable, like in practice a lot of functions are, you you can draw a tangent line, and then you have another graph here. So a tangent line is also a graph of a function. It's the function which I'm going to call y equals L of x for linear approximation. And the only moral to the story is that this is pretty close to y equals f of x. And the approximation is better if I call this point A. So one important topic is deciding how good or bad this approximation actually is, which I'm not going to get into. But of course, if you're in your life, you want to know, you want to approximate things by easier things, and also you want to know how bad you did. But the thing is, if I look at this portion of the, if I look basically at the whole function, well, here it's not very close. Here it's not very close. But as they get closer, they get the function and the line, they get closer and closer, and I care less that I did an approximation. So so finding the linear approximation is the same thing as finding the tangent line. If you're confused by what I'm about to do and you're thinking, why isn't this just finding the tangent line? That's because it is. So how do you find the tangent line? The slope is the derivative, and it passes through the points on the graph. What is this point on the graph? Well, it has x coordinate A, and it's on the graph. So the y coordinate is the function applied to the x coordinate. And that would make the point A f of A. So the point slope formula for the line it's this thing, it's y minus the y coordinate equals x minus the x coordinate. So if the point is x naught, y naught, we subtract y from one coordinate, x from the other, and we multiply by the slope. And this is the graph of a function. To write it as a graph of a function, I should solve for y. So let me just write it again. So it's y minus the y coordinate equals x minus the x coordinate times the derivative, which is the slope. To solve for y, I just write y equals f of a, and maybe I like to write this order better. And that's it. So we call this function and notice that this is a linear function. I didn't do any complicated functions to x anymore. I added a number and I added another number and I multiplied by a number, which makes it a linear function. It's what you get when you only multiply your variable by numbers and add some other numbers. And that's it. So without getting into how close they are, I would say that a function is more or less equal to this linear function. And this is the linear approximation, and this is all there is to it. So
is linear approximation just point slope formula, really?
it's literally just that.
Okay, so it's just different letters.
Yeah,
Wait,
I would
so-
say, I mean, this is an equation. Here I wrote y equals something. This is a function, but that's it. It's not really a difference between an equation and a function. So
Wait, so weren't we doing that on like the WebAssign homework because we had to find the like derivative of the function and we had to plug in the points to find like the
I bet I don't remember everything that's on WebAssign, but probably you had to find the tangent line at points. Yeah. So yeah, you've already done this.
okay.
Yeah, I mean, I guess that you would be confused by what's the difference between this and what we've already done. And honestly, I'm confused too a little bit. But the thing is, what I've never, for example, this problem I'm about to write. This is a problem that, unless I made a mistake, has not been on your homework yet. Let's approximate the square root of 10 without a calculator. I mean, then I'm going to use a calculator to see how well I did. So the thing is, I want to understand the square root of x. If so, they didn't give me a function, but I made a function. And I want to understand it at x equals 10. But without a calculator, I don't know. I mean, maybe you remember how to take square roots, but maybe I don't. And also, it's going to be easier. It's going to be the same. I don't know. But the thing is, where do I know the square root better than at 10? That is close to 10.
9.
9, yeah. So let me try to draw a picture. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10. The thing is, I'm looking for what's happening here. And what I'm going to do is do the linear approximation at x equals 9. And these 2 points are going to be pretty darn close. And that's going to be good enough for me right now. So find linear approximation of the square root of x near 9. So a equals 9. So I'm just going to look at this formula and use that formula, and that's it. So I'm going to need the derivative, but you know the derivative. The derivative of the square root is 1/2 x to the 1/2 minus 1, which is 1 over 2 square root of x, which conveniently is easy to plug 9 into. The derivative at 9 is 1 over 2 root 9. So it's 1/6. And now linear approximation, this formula says you need to do f of x, so f of 9, which is the root of 9, and then add f prime of 9, which is 1/6. Times x minus a. So well, it's not equal. It's close. And this would tell me that f of 10 is 3 plus 1/6, which is, well, it's approximately 3 plus 1/6, which is 3.1667. So that's my guess for what the square root of 10 is. So how close were we? We're probably pretty close. We're closer to decimals, and all it took was adding 3 and 1/6. So if we had done 12 instead of 9, it would have been worse. The further you go from a, the worse it gets, but it's not bad at all, especially for not doing any work. SQRT is square root, by the way. And that's it. That's all there is to it. Any questions?
Wait, so do we pick 9 because that's the closest square root?
Yeah, that's why I picked 9. So it was a square. You could try picking 4. Actually, let's try picking 4. It's gonna be way worse. So the derivative at 4, the derivative, remember, oh yeah. Let's make a equals 4. The derivative I just said is 1 over the 2 square root. So the derivative of 4 is 1 over 2 root 4. It's 1/4. So using this linear approximation now, let me write it down again for you. In this case, the function is root of 4. The derivative is 1/4. Here I have x minus 4. So 2 plus 1/4 times x minus 4. So the root of 10 is supposed to be close to 2 plus 1/4 times 10 minus 4. And that's 2 plus 6/4, and that's 3.5. So way worse. So let's draw what just happened. So I have the square root of x, this function, and I said I wanna find the y coordinate of this point. So this is the point I'm looking for, and the first linear approximation I used was 9. So that's going to be f of 9 plus the derivative times x minus 9. So if you look at what happens around 10, what happens is that the line and the curve are very, very close together. And this is actually tangent at 9, but over here it's just very close. It's not the same, but it's close. If you try doing it at 4, which is the second thing I tried, well, you can see it goes a lot further away. So this was 2 plus 1/4 times x minus 4. So kind of similar looking, but now it's just further away. Around 4, it's really good, and as you move further and further away, it gets worse and worse. And by the time you get to 10, it's pretty bad. 10, 3.5. I mean, could be not that bad depending on what you want to do with it, but and that's it. That's all there is to linear approximation.
So there will be like other like would it happen with an equation that's like not square roots of stuff, or
Yeah,
always?
so I mean, for in general, a function that's complicated to find, for example, sine or cosine or exponential or logarithm, those kind of functions, you can try to do linear approximation, which is something you see very often. For example, the sine of x is close to the sine of 0 plus. So this is linear approximation of the sine of 0. The derivative of sine of 0, which is the cosine, times x minus 0. The sine of 0 is 0. The cosine of 0 is 1. So this is just x. So the approximation that the sine of x is close to x is something you see a lot. You see used a lot, basically in places where you're dealing with a very small angle and you don't want to do algebra with a sine. You want to make your life easier. So, and this is a really good approximation if x is very small. For example, look at the sine of 0.1. Sine of 0.1 is pretty much 0.1 up to the third decimal, the fourth decimal. Sine of 0.1 is pretty much 0.1. So you could do this for any function, but it's just always the same. And I mean, it's a big interesting question to know. That's just something you always want to know, how big an error you made. Because if you don't know, well, in practice it could be pretty useless. But we're not getting into that.
So how do we figure out which fraction to use?
Which fraction?
Like, do we just use like a Just one. Because like I don't know why you did like 1/6 instead of like 1/7, so you can be like more in depth with it.
Here, the 1/6.
Yeah.
This is the derivative.
Oh.
Uh,
Okay. There we go.
the slope is the derivative. So the
All
thing
right,
with the
sure.
derivative is that it's the best number to use there.
All right. Thank you.
Would it be inaccurate to say that this is basically just a tangent line? Like if like
No.
they asked us.
You wouldn't. I think it's fine. All I want you to realize is that the tangent line is a very good way to approximate the function. Okay. There's no more questions. I'm gonna talk about 3.11, which is also not gonna stop on at all. So 3.11 is hyperbolic functions. So hyperbolic functions are just some functions that you have all the tools for knowing to know, and they have a name because they're useful, and they have nice properties. So hyperbolic functions are hyperbolic sine and cosine. So they don't have a lot to do with sine and cosine, except that well, it's relative. What they don't you don't need to think of them as having anything to do with sine and cosine, except that they have the same name. So hyperbolic sine, which we write sine h for hyperbolic, is just this function. Hyperbolic cosine is just this function. And anyone want to guess what hyperbolic tangent is?
Plus or minus.
Plus or minus? It's not plus or minus.
Would it be e to the x minus e to the negative x over e to the x plus e to the negative x?
Yeah, that's exactly what it is. So if I call it tangent, that must mean because it's sine over cosine, and sine over cosine is exactly what Autumn said. So sine is this, cosine is the other thing, the inverse means putting the fraction upside down, and that would make it e to the x minus e to the negative x, e to the negative x. So I'll talk a little bit about them tomorrow, and then I'll move on. Basically, you've seen a hyperbolic cosine in your life. I don't know if you recognize as having seen it, but this is hyperbolic cosine. It's the shape a hanging cable makes. So I have so many cables.
What are they used for? I've never.
What are they used for? Well, some nut job architect made an arch next to the Mississippi in St. Louis with this shape. That's to start with. So honestly, I don't know a million applications of hyperbolic sine and cosine. I know a couple, but anyway, this, if the cable was not rigid, which it is, so this is terrible. It doesn't look like hyperbolic cosine at all. Not a cable. It's also super twisted. This is supposed to be, it's supposed to make the shape of hyperbolic cosine. So if you're, for example, say you're building a hanging bridge, Let me draw. The thing is, now you're starting to quiz me on my physics, and I don't know my physics. This is probably a pretty good shape to make a bridge out of, because it's the shape that the cable naturally wants to make. So that's one reason. In calculus, it's just, well, I want to have more functions to play with, basically. Those are supposed to be cars. Anyway, that's it. I'll tell you a little bit about them tomorrow. That's all I got for today.